Welcome. This is 48A video 3, and we're going to talk about dimensional analysis. When I was a student and I first came across dimensional analysis, I don't think I really got it. It just seemed dry and a bit pointless. But now that I'm more experienced, I realise that it is kind of a very interesting part. Sometimes when we talk about units, we find that, for instance, impulse, which has units of Newton seconds, is equated to change in momentum, which has units of kilogram meters per second. And they're different units, but they're equal to each other. And the reason for that is that the units have the same dimensions. So rather than talking about units, we prefer to talk in terms of dimensions. So when we talk about lengths, we talk about an L inside square brackets. So the unit could be meters, but we're thinking about a length. When we're thinking about a mass, we have an uppercase M inside square brackets. And when we're thinking about time, we have an uppercase T inside square brackets. So the symbol is not uppercase T, it is uppercase T inside square brackets. And sometimes people drop the square brackets and it gets quite confusing. The square brackets tells the reader, oh, we're talking about dimensions. What we find when we look at equations and math in general is that you can only add or subtract things that have the same dimensions. There's no point in adding the number of birds to the number of automobiles. Nobody would ever want to know that combination, and it would be a meaningless number. But adding the number of birds in one place to the number of birds in another place gives you a summation of the total population of birds. That's quite useful. So we can only add or subtract things that have the same dimensions. So that means when you have an equation and it's y is equal to mx plus b, the y must have one dimensional identity. It must be the same as the mx's dimensional identity, which must be the same as the b's dimensional identity. They've got to be the same kind of thing. You must have same dimensions on both sides of an equal sign. I just mentioned that. And you cannot tell the magnitude of a coefficient. Let me give you an example of that. Let's use a real equation. So kinetic energy is equal to 1/2 mv squared. And I know that kinetic energy is like work, and work is a force times a distance, which would give me the same thing as 1/2 mv squared. And force, I'm going to go over here now, and force is equal to, well, it's going to be kilogram meter per second squared times meters, and that must equal, well, mass is in kilograms, and then velocity is in meters per second, and that is squared. So this is going to be kilograms meters meters squared per second squared. There's meters squared per second squared with kilograms. So this side has the same units as that side, which means it's got the same dimensions. But what we couldn't get to is this 1/2. So dimensional analysis is great for saying, does this make sense? Is it possibly correct? And the answer is yes, it is. But what it has a blind spot on is it can't tell you about a coefficient. Should it be 1? Should it be 1/2? Should it be 2/5? It cannot tell you that. Coefficients themselves are dimensionless. They just disappear from the analysis. So we'll get to that in a minute. Scientific dimensional analysis gives us insights. So for example, fast food restaurants famously introduced skinny fries. They taste great, but they're also very easy to cook. And this is why they're very easy to cook. If you take any object and you give it an increase in dimension, let's say we're going to double its height, its width, and its depth. If we double the linear dimension of an object, if you think about it, if I double the height and the width, double the height, double the width, I have 4 times the area. And if you think about it, if I double the height, double the width, and double the depth, I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 times the volume. So if I double the linear dimension, I get 4 times the area, I get 8 times the volume. If I tripled the linear dimension, I would have 3 times 3, which is 9 times the area, and 3 times 3 times 3, which is 27 times the volume. So these ratios can make a big difference. Here's what's going on with the skinny fries. By basically, well, let's take it the other way. Big potatoes cook slower than small potatoes, because if I double the size of the potato, I have 8 times the volume. So I have 8 times the amount of potato to cook, but I've only increased the surface area of the potato by 4 times. So if I need 8 times the energy to cook the potato, but I only have 4 times the surface area, it must take twice as long. And if I did 3 times as big a potato, I'd have 27 times the energy needed to cook it, and yet I'd only have 9 times the surface area for the energy to go through, and so it takes 3 times longer. So by using skinny fries, food technologists realized they could cook potatoes very quickly. Same thing goes for cells, actually. If a cell is such a useful biological system, why don't we find cells just rolling around the streets like basketballs? I mean, if it's a good system, then why not have that? And it turns out, let's do it 5 times. So if I 5 times the linear dimension of the cell, then I have 25 times the area, because it's 5 times 5, and I have 125 times the volume, because it's 5 times 5 times 5. What that means is that I have, well, the volume determines how much animal I have to feed, so I have 125 times the hunger. But again, it feeds through its surface skin. I drew little mouths on here, but this was a joke. It feeds through the surface skin, and so I've only got 25 times the surface area. So 125 times the hunger, 25 times the surface area. It's going to take 5 times longer. It would require 5 times longer to feed itself, but it doesn't feed and stop feeding. It feeds itself as much as it can, and so it's starving to death. And so what happens is it says, I'm unhappy, I'm going to divide. I have a bigger surface area to volume ratio, and I can feed myself. So cells do not get hugely big. They reach a maximum value and then divide. And then, so here's another example on movies. As an engineer or a scientist, you realize when you watch movies, you watch them differently from everybody else. In the horror movies, when you get spiders the size of buildings, they were very popular around about the 50s and 60s. When you get spiders the size of buildings and they look very fearful because of the photography, it turns out all the physicists and engineers are laughing, because here's what happens. Let's say I increase the linear dimension of the spider by 10 to the 2. I make it 100 times taller, 100 times wider, 100 times deeper. Well, that means I increased its surface area by 10 to the 2 times 10 to the 2, which is 10 to the 4. And I increased its volume by 10 to the 6. Now, what does that mean? That means that it's 1,000,000 times heavier. It's 1,000,000 times heavier. But it turns out the strength of an animal depends on the cross-sectional area of its muscles, not the volume, but it's the cross-sectional area of the muscles. And so I'm only 10,000 times stronger. So I've got 1,000,000 times the weight to hold up, but I'm 10,000 times stronger. It means that I'm going to have effectively 1/100th my normal strength. And so a spider the size of a house would lie on the floor gasping. It would not be able to function. You cannot just increase the dimension of something and have everything work the same way. You've got to take into account the dimensional shift. So that gives tremendous insight into the physical world. I think it's a really, it's difficult to ask questions about that, but I think it's a really insightful part of dimensional analysis. This is what you tend to be asked about, and frankly it's not as interesting, but it is useful. Show that dimensions of a parameter S, length squared over, that should be, I'm sorry, oh, I didn't spot that, that's a time. There's me thinking in units. Over time squared times mass, given the equation. So what you say is, well, the dimensions of, let's write down the equation, it's 5v squared over m, where v is velocity and m is mass. So the 5 goes away, so forget about it. And the velocity, well, it's meters per second, so that's going to be a length divided by a time, but that's squared, and it's over mass, and the mass, of course, is in kilograms, but it's just a dimensional unit of mass. I can't have a triple decker, and so I've got to first of all get rid of this equal sign, this square sign. Well, that's easy enough. That's going to be length squared, and that's going to be time squared. I did that bit, but it's still over this mass, and I can't have it as a triple decker. So the question is, do I divide by the mass? Does it go on the top or does it go on the bottom? And what I recognize is that's like m over 1. And so I end up with L squared over T squared. And then this thing flips so that the m is on the bottom. And there's my answer. So that's how you do them. And here's a follow-up for these. Let's have a go at this. So my equation is V. What's that going to be? That's going to be L over T. I forget the 2, of course. And then I have m squared underneath. Well, of course, I recognize that's like m over 1. So that's going to be L over T. And then m squared. So the correct answer to that would be C. You can't use units. I know I did up there, that was a mistake, but you gotta have this thing written in dimensions, and also that should be squared, and you can't have the lumber inside it. And there we have it. Thank you.